Welcome to the second part of the lecture about doing inference. We're going to start with doing statistical inference about the parameters. So remember there's the beta parameters. So remember there's two beta parameters that control the data generating process in the simple linear regression model. One is the slope, the other one is the intercept. And we can do either a confidence interval or a test about these underlying parameters. And we'll start with a confidence interval. Basically what we're doing here is we are coming up with a range of values that we think are reasonable statements to say about the simple linear regression model generating process, like, for example, the slope. What do we think the generating system mean function slope was? Well, we don't know, but we have some idea from the observed data about what might be reasonable to say about it. And what's reasonable to say about it is to take the estimate that we get, the beta hat, from our observed data, go above and below it, plus or minus, an appropriate multiplier from the t-distribution, where the t-distribution has n minus 2 degrees of freedom. We'll talk about that. And then we use the standard error that we get from our R output to take the variation and get the appropriate variation for that beta hat. And this is going to produce a range of values that are reasonable things to say about the underlying generating system. The other way we do statistics is through a hypothesis test, where we have a null hypothesis in H that a beta parameter is equal to some value against an alternative hypothesis that the beta parameter is not that value. And we construct a standardized t-statistic like this one. We'll have an estimate minus the hypothesized value over the standard error, and then we'll compare this to a t-distribution to make an inference. Most of the time this value that we're comparing against is probably a value that would be 0, but we'll talk about that in a later overhead. So here is how we might do this and see this in R. You'll notice that in R we get an output table from a model. We've talked about the estimate column. We've talked about the standard error column. And then here is a value of a t-statistic. And then here are p-values that we'll need to talk about in this presentation. Down here in the commands box, I go through excruciating detail about how to come up with a confidence interval. And this is not something I would recommend that you do. I just want you to notice that if you try to follow this, what I'm doing is I'm taking the second coefficient in this table, in other words, this duration beta 1 hat estimate, and I'm going below it by a multiplier from the t-distribution with the right degrees of freedom, and multiplying it by the standard error. And that's what this is doing. And you'll notice I come up with a lower boundary of 0.166. I come up with an upper boundary of 0.187. And I want you to notice that that is the same thing you get if you use the confidence interval command called confint. You will not do these first two commands, but I just want you to see that if you do the formula for a confidence interval out in full glory, like I'm saying here on overhead 28, you get the same result as if you use the confidence interval command. So I'm stressing the confidence interval command and suggest you use that. You use the confint command, you put in your estimated simple linear regression model from R, Old Faithful mod. You specify the confidence level you want for your confidence interval, 95% for example, and you come up with lower and upper boundaries for the slope coefficient on the bottom and the intercept coefficient for the top. And what you can see from this is, let's talk about the slope for example. You can see from this that on the second bullet here on overhead 30 that there's clear evidence that the slope or the rate of change between duration and interval is a positive number. All of the reasonable things to say about the data generating beta 1 parameter value is that it's something in between about 0.16 and about 0.19. And all of the things that are reasonable to say about that number are positive numbers, suggesting very clear data evidence that there is an increasing relationship between these two variables. The longer Old Faithful erupts, the longer you're going to have to wait for the next eruption. And so these are the ranges of what are reasonable to say about the beta naught parameter, something between about 31.6 and 36.3 minutes, and the duration slope is somewhere between about 0.166 and about 0.187, and this is how you produce confidence intervals using R. To take a look at one of the tests, we'll use the estimated slope parameter, and we'll construct a null hypothesis here that the slope between the two variables is really zero. This null hypothesis means that the data generating mechanism has no relationship between x and y. The slope of that relationship is zero, or in other words, no relationship. That's what we'll suppose in the null hypothesis. The alternative hypothesis says, no, this slope isn't zero, it's something else. There is a relationship going on. We don't say what it is, but there is one. Well, let's examine this null hypothesis. Let's presume it's true, and that means the value we want to test against is zero. And so we will use the beta 1 hat estimate from the summary table in R. We'll subtract off the value of 0 from the null hypothesis. We'll divide by the standard error from the R output. We come up with a t-statistic of 33.05. And if you notice back on the output, you will notice that is the t-value column, 33.05. The next column tells us about the p-value. And how do we get that? Well, we need to find the probability that we could observe a t-statistic more extreme than 33.05. And that would be the chance of a t-value being bigger than 33.05 or less than negative 33.05. And because the t-distribution is symmetric, we only need to look up the upper tail of the t-distribution and just multiply that by 2, which will give us the same probability in the lower tail. And so the upper tail plus the lower tail is the same as just taking 2 times the probability that we would observe something like that greater in the upper tail. And you'll notice that if you calculate that probability, it is exceedingly small. And on the next page, we'll talk about what that means. Small p-value means that the data we've observed is very unlikely to occur under the conditions of the null hypothesis, that there's no relationship. So the data we've observed is very incompatible with that null hypothesis. The null hypothesis is just not reasonable to generate data like this. And so in the third bullet, there's evidence to doubt the null hypothesis. There's evidence to support the alternative. And that means because the estimated slope coefficient was a positive number, we've got very clear data evidence that there's an increasing relationship in the underlying data creation system. Longer eruptions mean longer waiting times. Another thing we might want to do, other than doing tests and confidence intervals for one of the beta coefficients, is to do some kind of a prediction. How much is y going to be at a particular value of x? Or how much is a typical value of y going to be at x? So there's really 2 kinds of questions that are relevant here. Do we have a question about what the average value of y is going to be? Or are we asking what a single value of y is going to be? That's what I'm talking about in these 2 bullets. Are we going to try to make statements about what typically happens to y, or about individual values of y? So let's go through it. If we're going to talk about what an average value of y is going to be, turns out that a good estimate for the average value of y is just the estimated value from plugging in x into the least squares line. That's what y hat means. It's a fitted value or a predicted value. What it means is you'll plug in a particular value of x, out will come an estimated value of y from the estimated equation, and what we know is that on average that kind of an estimate is going to produce the mean function. It'll produce on average the right thing for the estimated value of y when x is equal to little x. That's what this vertical slash here means. What is the expected value, e, of y when x is equal to x? Turns out that this plug and chug prediction on average is the right value. It's the mean function. Here is the expression for the uncertainty of that kind of an estimate. You'll notice it involves the error variation, the randomness in the system. It involves the amount of data that we have, the number of data values, n. It involves the spread in the predictor values. And it also involves how far the value of x is from the average value of x. And if you think about this, what it means is that if you predict what y is going to be, or the average value of y is going to be, at a very strange extreme value of x that's either really big above average or really small below average, it increases the variation and the uncertainty in your estimate. And I think that makes sense, that if you're trying to estimate away from where you have a lot of data and values of x, you will typically not do as well. I think that makes sense. Here's how you do this in R. You use the predict command, you use the simple linear regression model object, and then you tell R what value you want to predict at. So in other words, what I'm doing here is I'm making a little temporary data set, data frame, that has one value in it, duration of 150 seconds. What should I expect to happen when the last duration was 150 seconds? I'm going to give it the option of interval equals confidence, and this option means I want to make statements about what the mean function of y is going to be, and we'll make a confidence interval with 95% confidence level. And so we get output that looks like this. The column called fit means that this is y hat. This is how much we should expect to wait, 60.5 minutes. Here is what the lower reasonable bound is for the mean function. Here is what the upper reasonable bound is for the mean function. And so what we're saying is that the mean function could reasonably be as low as 59.5 minutes and as reasonably big as about 61.5 minutes. And so what you can see is that we have estimated this mean function really quite well. Our level of uncertainty is really only about 2 minutes from the lower boundary to about the upper boundary. We're pretty sure what the average waiting time is. It's about 60.5 minutes plus or minus about 1 minute. That's what we're finding. However, sometimes we're not interested in just the mean function. We're interested in how long are we going to have to wait? An individual response value, an individual value of y. What is an individual waiting time going to be like? Well, that's a slightly different standard deviation. Our data estimate is really going to be the same. We're just going to plug into the least squares line and get a y hat estimate. But what we have to acknowledge is that since we're interested in an individual waiting time, there's individual observation variation above and below the mean function that we need to take into account. Even if we knew the mean function perfectly, an individual instance is going to have variation above or below that mean function, and we need to take that into account. And if you look at the standard error formula, you'll see that there's an extra 1 inside of it that is not present in the standard error formula for estimating the mean function. And that comes from the fact that when you factor inside, this sigma goes inside, you have an extra value of sigma squared, essentially, going on in the data generating process. And so this standard deviation for an individual value of y, the uncertainty in it, is always going to be a little bit bigger than what the uncertainty is for just estimating the mean function. If you're going to do this in R, you'll notice it's the predict command again. The simple linear regression model object, OF mod, goes here. We're going to predict at an eruption of 150 seconds. And the option changes to prediction. If you're interested in trying to say what an individual eruption waiting time is going to be, you have to put in the prediction option. You'll notice what happens to the output. The estimated single best value of how long you're going to have to wait is still 60.5 minutes, just like it was previously. This is the best single number that you can give for how long you're going to have to wait. But notice that because we're talking about an individual eruption, individual eruptions could turn out to be quite soon, which means that the lower limit for how long you'd have to wait is about 49 minutes. But you might have to wait as long as about 72 minutes if we get an abnormally long random error draw and we have to wait a long time for that particular eruption. This is the confidence interval that is relevant to a family that's walking up to Old Faithful and they want to wait to the next eruption. And the last eruption was 150 seconds. A family should presume that they're probably going to have to wait between 48 and 72 minutes. So that's quite a bit of uncertainty and variation in what's going to happen to an individual eruption. You remember that on average, we had a pretty good idea that the eruptions are going to happen between about 59 and 61 minutes. But for individual eruptions, it's quite uncertain. And that's really the distinction here in the predict command. Here's a demonstration about that difference in variation on overhead 38. The solid boundaries represent how much uncertainty there is for an individual eruption, and the dashed boundaries represent the uncertainty we have in what's going on with the mean function. When we have a lot of data like we do, we really are quite confident about where the mean function is. But that really doesn't help us resolve the variation in what an individual eruption is going to do. That is controlled by the sigma parameter, and we don't have a way to deal with that other than that it exists in the random system. We're going to talk a little bit about an f-test right now, and this really doesn't accomplish anything different than the t-test for the estimated, for the slope parameter in the simple linear regression model. If you look at what we're testing here, we're testing a null hypothesis that says that the mean function is just a constant against the fact that the mean function is a function of x, and that this slope parameter is not 0, that there is some kind of a relationship. You can test this kind of hypothesis with an f statistic, where we take the mean square for the model regression, we divide it by the mean square for residual, and we come up with this f ratio, this f fraction. And from that value of f, we can construct a p-value, and we'll use the f probability distribution. And the f probability distribution is a very skewed right distribution that starts at 0 on the left and extends out in a long right, skewed right tail. And we can find the appropriate p-value by finding the chance that we could get an f random variable bigger than this computed f statistic. If you've not seen the F distribution before, notice that there are two sets of degrees of freedom for this F distribution. The first degree of freedom index comes from this numerator. What is the degrees of freedom for the mean square regression? Well, it's just 1. And the second set of degrees of freedom comes from the denominator, the degrees of freedom for residual, which is n minus 2. And from this p-value, you can make the appropriate decision about the null and the alternative hypothesis. A small p-value is going to mean that the data is really incompatible with that null hypothesis and will suggest evidence that there's a relationship. A big p-value is going to mean that the data we've observed could quite reasonably be from a data system that doesn't have any relationship. And so we can't rule out a no relationship data system. Here's a picture of what the two hypotheses look like. The null hypothesis says that the data generating mechanism is some sort of horizontal pattern with no trend. The alternative hypothesis says that, well, there is some kind of trend in the data. And the question is, does the data strongly suggest there's a pattern or doesn't it? And that's what that p-value for the f-test says. We can get everything we need for this f-test from the ANOVA command that you've seen before. It partitions the variation into the part for the regression model, this first row, and the part for residuals, the unexplained part that is in the second row. And you'll notice we get an f value over here in this column and the associated p-value in scientific notation over here in the far right column for p-value. So sketching it through here, we have a null hypothesis, we have an alternative. I put in the appropriate sum of squares, the appropriate mean squares, and we get the F statistic of 1092, like we see here in the R output. And the p-value is amazingly small. The chance that you'd get an F statistic bigger than 1092 is practically zero. It is an extremely small chance. And so we've got lots of incompatibility between the data and the null hypothesis. You just couldn't get data like this being generated from the null hypothesis conditions. So there's doubt about the null hypothesis, there's support for the alternative, and that means there's support for a relationship between the two variables. Finally, one thing you can do to examine your simple linear regression model and decide if it's a reasonable thing to be using to make statements and inferences is to do what's called a residual plot. And the residual plot basically plots the residuals for a model on the vertical axis and the y-hat predicted values on the horizontal axis. I've added in a reference line of 0 here, remembering that a residual of 0 would mean that that data value is almost exactly predicted by the least squares summary line. What you're looking for here is basically a good model would have residuals that are randomly scattered above and below 0 with no particular curved trends or patterns. And this particular residual plot shows that there really is, this is a good looking residual plot. I don't see any particular patterns in the residuals as I move from small predictions to big predictions. I see just random scatter around 0 and about the same scatter around 0 no matter where we are in the plot. And that's a signal of a really good looking residual plot. I hope this video has helped you get ready for study and homework problems.